The next chapter, chemical kinetics, is very important for the MCAT. Chemical kinetics is all about the rate of a reaction, or in other words, the speed of a reaction. Now there's many ways, or many different types of data that can be given to us, and we have to extrapolate and immediately think, what is the rate law? Now if they give us an equation, okay, and it's one-sided, meaning there's an arrow pointing in one direction, we can easily determine the rate law as the concentration of the reactants to the power of their coefficient. Okay, so if we're given this formula or this chemical reaction, we can immediately write the rate law as the concentration of A times the concentration of B, but because there's a coefficient of 2 next to the B, we have to square that in the rate law. And that's a simple rate law. You just take the concentrations of the reactants and whatever coefficients in front of them, put that as the exponent. Okay? And again, we can only apply this simple rule when we're dealing with a one-sided reaction, where all the reactants become all the products. Okay? So that's very simple. You can immediately just take the reactants. Now, sometimes they won't make it that easy. Sometimes they'll give you some data, okay, some experimental data. Now what's happening here? Well, basically, there's 3 trials. Scientists are conducting an experiment, and they try the experiment 3 times. And what they're essentially doing is they're starting with different concentrations of the reactants. Okay? And from those starting concentrations, they're then determining the rate of the reaction. Okay, very simple. Now, if you're given this type of data, or in a table, we have to immediately come and think of this same rate law. Okay? And how do we do that? Well, basically, they're giving us 2 initial concentrations. We basically have to compare each trial where one of those concentrations, for example, A, doesn't change, and now we have to see how B changes. Okay? And from that, we then look at how the rate changes. And then we can determine what type of exponent we're going to put in the rate law. So let's take trials 1 and 2. What happens? Well, in trial 1, everything was 1 molar. Okay, a molar is just moles per liter. So 1 molarity of each A and B, and the rate is simply 20. Okay, 20 molarity per second. All right. Now what about trial 2? What happened? Well, we kept a concentration of reactant A the same, 1 molarity, but we doubled the concentration of B. Okay? So if we double the concentration of B, now what happens to the rate? Well, it actually quadruples. It multiplies by 4. Okay? So that's a little bit different. If we plug in a 2 and multiply concentration of B by 2, rate quadruples. That's a square function. Okay? If we replace B with just a 2, what does that mean? It means 2 to the power of 2, which is 4. Rate quadruples, multiplied by 4. Okay? So does it make sense why when we put, for the rate law, when we write in the rate law, we're going to put rate equals K. K is the coefficient. We'll talk a little bit more about that in a second. Times concentration of B, we've got to make sure we put a 2 there because it's squared. Okay? So again, if we double B, it quadruples the rate because 2 to the power of 2 equals 4. Okay. Now what about A? They gave us A, so let's see what happens to A. Well, from trial 1 to trial 3, concentration of B stays the same. Okay, we have to find the trials where they stay the same. Now what happens to A? Well, A doubles from 1 to 2, so how does the rate law change? Rate also doubles. It goes from 20 to 40. So if A doubles and rate doubles, that means they're directly proportional. We're just going to leave an exponent of 1 on the A. Okay? So again, if we substitute a 2 for A, rate law also is multiplied by 2. So they're directly proportional. Okay? And that's how we can figure out a rate law from table experimental data. Okay? Now, we know rate equals K times A times B squared. Now this is just one example of a rate law. There's many different rate laws that you will see on your MCAT. K is the constant which you multiply by these concentrations to get the rate. Okay? Now, you don't have to worry much about K, but you should know the Arrhenius equation, which is a way to calculate K. Okay? Now, even though the rate of a reaction and K are not the same thing, we know that rate is proportional to K. Okay? And that should be pretty evident. They're proportional. Now, K equals the Arrhenius equation. Okay, and you should understand the Arrhenius equation. Zp times E to the power of negative EA divided by RT. Okay? Z and P are just constants, same as A. Okay, so we could replace Z and P by A. You can see the Arrhenius equation written in multiple forms. The important part is the E. Okay, E is very important. It equals close to 2.271. But the important thing is the exponent. Okay, negative EA, that's the activation energy divided by RT, and that's an entire exponent. Now the rules with exponents are a little bit different. Basically, you're going to want to remember as the denominator increases, okay, the rate constant K also increases. So it's in reverse because it's a negative exponent. So just keep that in mind. Similarly, EA, which is activation energy, as that decreases, K increases. Okay. Now, this all has to do with collision theory. This is outlined in your final review guide. We'll talk more about it later, but it's very important to just understand it's those normal rules we think of. It's kind of reversed because we're dealing with a negative exponent. Okay. In conclusion, you want to remember rate of a reaction increases with increasing temperature, and rate increases with decreasing activation energy. Okay. All right. Next, once we have our rate law, okay, they could ask you something called what is the order of the reaction? In other words, what does this reaction depend on? How many species of reactants does this reaction depend on? And it's very simple. You just add up all the exponents. As simple as that. Okay? Now, if we add up all the exponent and it's equal to 1, this is known as a unimolecular reaction. Okay, we'll see more about this in organic chemistry, but it's known as a unimolecular reaction. Now, if we add up all the exponents and the order of the reaction is 2, then we have something called a bimolecular reaction, where the rate of reaction depends on 2 different species or 2 different reactants. Termolecular is when the rate of a reaction depends on 3 species. Okay, just like we have up here. If you add up all the exponents, we have a 1 on the A, we have a 2 on the B, total of 3. This is a termolecular reaction, depends on 3 different species. Okay, and by species we just mean molecules. So 1 A molecule and 2 B molecules. We have to have all of that for this reaction to proceed. Okay, again, that's known as a termolecular, order of 3. Okay. Now sometimes you might have a reaction where if they might give you data and changing A, maybe doubling A, doesn't change rate law at all. Okay, rate will just change, will equal the same number. If rate equals K and that's it, meaning any changes to these other reactants doesn't change rate, we have something called a zero order reaction. Okay, zero order, where rate is independent of any reactants. So in other words, rate equals K, and that's it. Okay, it's a zero order reaction, where no matter what changes we do to A and B, rate stays the same. All right? And then finally, we have something called a pseudo first order reaction. Okay, this is a little bit different. This is a special scenario. You might have 2 different reactants like A and B, but in this special scenario, one of those reactants, we'll say B, is either a catalyst or is an extreme excess. Okay, we just have so much of it that it really doesn't all react. The important molecule in that case is A. It's almost like a limiting reagent. Okay, where only the amount of A matters. So in other words, we can write this reaction as K times the concentration of A. Okay, so again, that's where B is in huge abundance and excess, or it's just a catalyst. It's not involved in the reaction, but we still need it. Okay, so in that case, we don't care what the concentration of B is. We can ignore it. And now it's just K times the concentration of A. This is known as a pseudo first order reaction. Okay, because originally it was second order, but because we ignore one of them, it's now back to a first order, known as pseudo first order. Okay.